So when we left off on our last tutorial, we were talking about problems where we can use the second law of motion with torques. More specifically, talking about a problem where we had a force that was causing a wheel to rotate, and we calculated torques, we calculated the moment of inertia, and we figured out the acceleration. So what we want to do is look at a slight variation of this problem, and in the process do a general derivation that's going to be important for future problems as well as the lab. So you want to pay close attention to the derivation and make it accurate. So the problem is similar, but instead of a constant 1.5 Newton force from some unknown object, we're going to use a falling mass that has a weight of 1.5 newtons. And we're going to see that the solution is a little bit more complicated because of the fact that we have an upward tension to account for, whereas we didn't really have it there. The tension was the 1.5 newtons. So to give this its full due, let's turn to a general description of this problem where we have an object, we'll call it a mass, okay? And it is trying to rotate a pulley of a radius r. The pulley has its own mass, we'll call it little m. And if we complete our force diagram, and that's a key here, and I want you to think about that carefully, what forces are acting on our system. Our system is now the pulley, which has mass, we can't ignore it, as well as the falling mass. So, of course, we're going to have a tension upward, and by the third law of motion, we have to have a tension downward. And this downward tension is significant because that's the force, or going to apply the torque on the pulley. That's what's going to make it rotate. We also have forces on the pulley. We have its own little weight, we'll call it mg, and it's not falling down, so there's something holding it up. Let's just call it some upward applied force. You want to call it the normal force, that's fine, but that's not the issue. Okay, so we've got our forces. We've got two things accelerating. We've got the block that's accelerating linearly, and we have the pulley that's rotating or accelerating rotationally. And so we got to come up with two sets of equations, one for the linear, one for the rotational. And that shouldn't be too difficult for us by now. So if I take the block one, it's pretty straightforward. That big mg, it's accelerating down, so I'm going to call this my up force minus t is going to equal big M times A. Okay, now I know ahead of time that I want to solve for tension because that tension is important for the torque. So if I rearrange this, I see that the tension in the pulley is going to be equal to mg minus ma. Okay, so we'll come back to that. So I'm going to kind of box that for now because that's a significant little piece that we're going to need later. Now let's look at the torques. So I have a torque that's right along here. I have a lever arm that is the radius of the pulley. So in terms of tau, in my general formula, is I times alpha. All right, I'm just substituting for tau. The torque times the radius is going to equal I times alpha. Okay, so that's a pretty significant equation right there. It's pretty simple. Okay, if I were to change the tensions on there by changing the mass, I would see, and I would plot alpha, I would get a linear relationship there. Okay, so let's continue on. So the rest is really just substitutions. Notice in both equations, I have a tension vector, or the tension component, and then I have an alpha and an A. So I want to bridge between those two. Okay, so I'm going to substitute in the torque equation, I'm going to take out the t and put in mg minus ma. So I'm going to say mg minus ma times r equals I alpha. And then I don't want A and alpha in the same equation, so I'm going to say A is equal to alpha r. Right? We know that relationship from kinematics. That's a very important relationship. So I can substitute that in, and now I have mg, I'm going to distribute the r minus m alpha r squared. Okay, so I took out the a right here, put in alpha r, and then multiplied by this r. That's where I got the r squared equals I alpha. All right, so what I'm going for here, maybe we didn't make this clear, is what's the angular acceleration of the pulley. Okay, so we've got everything that we need. We just got to do some algebra. So I'm going to move the ma alpha r squared. So I have mgr equals I alpha plus m alpha r squared. And if I pull out the alpha, I have alpha I plus mr squared. Okay, so solving for alpha, alpha is going to be equal to mgr all over I plus mr squared. All right, so that's really our main result there. Okay, but we can take it one step further, and that's where we want to finish. So I'm going to box this off because that's an important general solution here. Okay, now what's this I? Well, this is the moment of inertia of the pulley itself. So we can substitute an equation for that because the pulley has a particular shape. So the pulley is a disc, a rotating disc. So we can look up in our notes that the moment of inertia of a disc is equal to 1/2 mr squared. Okay, so now we can substitute in for I. Let me extend this down a little bit. And so now we have alpha is going to equal big Mg times R. Now, for I, we got to be careful. It's little m. It's the mass of the pulley, not the mass of the falling mass. Okay. Oops, I forgot the 1/2 r squared plus mr squared. All right. I can't add the two terms in the denominator because I have two different m's, but I can pull out an r squared. So this would become mgr all over r squared times 1/2 m plus m. And I'm just going to do one more thing. I'm going to do two things. I'm going to multiply both by 2 over 2 because I can get rid of that half. And I see that the part r comes out. So I'm going to have on top 2mg all over r times m plus 2m. Right? When I multiply the denominator by 2, that canceled out, but I got to distribute the 2 through there. So there is our final solution for alpha. And now we can go back to the problem we were talking about at the beginning and put in the numbers. I'll leave that to you to do. If you do it correctly, and you should verify this yourself, you should find that alpha is around 120 radians per second squared. Okay, so this derivation, it's a lot of algebra. Look at the key substitution we're making. Look at the parts that I have boxed because they're going to become important later.